going to talk about Lie zeros on bounded degree graphs.
Thank you, and thanks for the opportunity to give a talk here, and it's nice to be here at the Simons Institute. Yeah, so I'll be talking about Lie zeros and the complexity of the ferromagnetic Ising model on bounded degree graphs. This is based on joint work with Piotr Buys, who is at the University of Amsterdam, Andreas Galanis at Oxford, and Veeresh Patel, also at Amsterdam. And this work fits into the broader line of understanding this idea of absence of zeros for partition functions leads to efficient approximation algorithms that we've seen at a couple of times now, the past week, but also, of course, in the original workshops. And the question is, what happens? Is this an if and only if? And what is the relation between the existence of zeros and maybe the failure of efficient algorithms? So some people have already looked into this. In particular, Bezakova, Galanis, Goldberg, and Stefankovic, they looked at this for the independence polynomial and the matching polynomial. And for the matching polynomial, in fact, they show that, so it's known that for the matching polynomials, the roots are on the negative real line, and all the way up to the zero freeness, they show hardness of approximating the matching polynomial. So you could say that existence of zeros and absence of zeros, they really indicate algorithmic tractability there for the matching polynomial. For the independence polynomial, it's more subtle. I will get back to that at the end of my talk when I go to open questions and things. And this brings me to the topic of this talk, and that is the ferromagnetic Ising model. And so I will tell you some things about it. So let's first go to, so let's see, I'm somehow checking whether I'm, go to the definition of the partition function. We have already seen it a couple of times during the last few days, but let me just make sure that everybody is on board here. So we have two parameters, lambda and b, and then we define the partition function for a graph G as the sum over assignments of pluses and minuses to the vertices, and then we raise the lambda to the number of plus vertices, and we raise b to the number of edges whose endpoints have received different signs. So typically, in statistical physics, the lambda would be some e to the 2h over 2, where h is some external field and t is the temperature, and b would be e to the 2j over t, where j is some interaction parameter. But by changing coordinates, we can think of this just as in terms of lambda and b, which is maybe slightly more convenient. And so Will just gave a very nice talk about statistical physics and how what kind of problems arise there. And this model is one of these lattice models that was invented to study ferromagnetism. And somehow, very surprisingly, I recently learned last year that it even finds applications in theoretical psychology to model psychiatric disorders. And so I was very surprised to learn that. So this has very many applications and far beyond statistical physics. And let me also mention that so typically people, well, I don't have to explain here that non-real parameters are interesting. But from the algorithmic perspective, one may wonder why would you want to compute this quantity for non-real lambda and beta, or lambda and b. Well, this is related to quantum output probabilities of quantum circuits, as was shown by Ryan Mann and Bremner. And but also there's other relations to quantum, and I will get to that in a second as well. Somehow very surprising. And so this talk, I will focus on the ferromagnetic case, as it was announced in the title, which just means that B is in the unit interval. And this will be the physically relevant case in terms of algorithms. I will look at that particular case. And yeah, so since this talk is about existence of efficient algorithms, or maybe non-existence of efficient algorithms, let me tell you quickly what or some things that are known for the Ising model. So a famous algorithm is the one by Jerram and Sinclair that shows that you have an FPRES, which just means that you have an efficient randomized algorithm to approximate a partition function, and this is in the ferromagnetic situation and for any positive lambda. And this is quite spectacular because it works for all graphs. And my talk will be restricted to bounded degree graphs. So just let me mention that by curly G delta, I'll denote the family of graphs of maximum degree at most delta. So this is there. We have this randomized algorithm, and then in a few years ago, Liu, Sinclair, and Srivastava, Pius came up with an FPTAS, which is a deterministic algorithm to efficiently approximate a partition function, and this works for B from -1 to 1, and any complex valued lambda which is not of norm 1. And we will see in a second why where this FPTAS comes from the perspective of zero freeness implies efficient algorithms. But let me just mention another result, which is due to myself and Han Peters, and that is that if you restrict your B to be in a small, well, very close to 1 here, then there is an arc on the unit circle where you have an efficient algorithm to approximate a partition function. So this allows for some lambdas where the norm of lambda is equal to 1. And here this delta is really the delta of the class of graphs we care about. The FPTAS of Liu, Sinclair, and Srivastava doesn't really depend on delta in the sense that the parameters don't depend on delta, except that for the algorithm to be running in polynomial time, you first have to fix the maximum degree. Otherwise, the algorithm would be quasi-polynomial time. All right, so let me state, so as I said, this is this randomized algorithm, so let me state the corresponding zero freeness results that go with the algorithms. And the first one is, of course, as Will also talked about, is famously by Li and Yang, and that says that if you fix your B inside this interval, then and you think of this this partition function as a univariate polynomial in the parameter lambda, then the roots of this polynomial, the zeros of this polynomial, lie on the unit circle in a complex plane. And then using the Barvinok interpolation method, you get immediately that inside the unit disk and also in the complement, you get the algorithm of Liu, Sinclair, and Srivastava. And then there's, so let me scroll down a little bit further. Then there's the other consequence or the other zero freeness implication for this other algorithmic result. And that's a result of Han and myself, is that if B is in this interval, then there is some symmetric arc on the circle for which there are no zeros for the partition function, hence by the same method we'll have an efficient algorithm. And let me finally mention another result concerning zeros, because these two results, the Liang result says, well, if you find a zero, it must be on the unit circle. This result says, well, you have an arc where there are no zeros. And then finally, this result, independently proved by Chio, He, Roeder, and myself and Han, it says that if you look at the complementary interval from this one, if you go to the left, if you go to the left, then the roots of this polynomial are going to be dense on the unit circle if you look at the roots over all graphs of maximum degree at most delta. So this result that says that we have this zero-free arc, somehow as B approaches this delta minus 2 over delta, this arc is going to shrink all the way down to a single point. Somehow saying that these two are somehow complementary results in a sense. And okay, so now we know a little bit about absence of zeros implies efficient algorithms, and here now we have a result describing where are the zeros. And of course, the question then is, what does it tell us about hardness? And before reading out the technical details, I will just tell you that it is going to be hard to approximate the partition function on the entire unit circle if your b is in this interval 0, delta minus 2 over delta. To state such a, and actually to prove such a hardness result, we have to be a little bit careful because we have to say what we're dealing with. So we take some number lambda, which is not a real number, so it's not equal to -1 and 1, and it is on the unit circle, so absolute value is equal to 1. But we also require that just 1 second here, that the real and the imaginary parts, that they are rational. So somehow that's important, because otherwise it's going to be hard to feed to say anything about computational complexity, and we need to look at the bit size of the input, of course. And then, so what is hard then? So the problem of computing a number which is an approximation to the absolute value of the partition function. So a 2 approximation, but the number 2 is kind of irrelevant. It could be any number. So that problem is sharply hard on graphs of maximum degree delta. And even if you further assume, if you restrict to those graphs for which you already know, which is given that the partition function is non-zero. So that in other words, I mean, if the partition function is 0, then this is not really well defined, of course, this approximation guarantee. So we may assume that the partition function is non-zero, and then you want to approximate the absolute value of the partition function, and that's a hard problem. Yeah, so let me just reiterate that this is exactly the region where zeros are dense on the unit circle. So you could think of this result as somehow saying, or giving evidence saying that, okay, existence of zeros somehow indicates hardness of approximating the partition function. I want to get back to this connection at a later stage after I tell you a little bit about some ingredients of the proof, and I will and then I want to discuss this connection a bit further. Let me just further mention that these rational numbers, or that these numbers on the unit circle with rational, real, and imaginary part, they are dense on the unit circle because we just have a rational parameterization of the circle. So that is really just, it really is hard on the entire circle. Just in case you were wondering. All right, so the next I'll give you an overview of the rest of the talk, and essentially I want to give you a few ideas of the proof. And essentially there are two main steps. So one is, and I guess this is standard in hardness, is that you have to reduce your problem to some problem for which you know it is hard. And what we'll do is somehow we'll reduce the problem of approximating the absolute value of the partition function to exactly computing a quantity related to the partition function. So somehow having access to this approximate norms of the partition function, we can somehow compute some other quantity exactly, and that hence the Sharpie hardness, because these things are hard in general. And we'll do this by implementing fields, and by implementing fields I mean just changing the vertex activity for one of the vertices and doing that in some kind of a clever way. And then the way we implement these fields is that we'll utilize chaotic behavior of certain associated dynamical systems, and I will also say something about that, and then I will get to some open problems and questions that are still there. Okay, so are there any questions or comments at this moment? In any case, if there's questions or comments, I'm happy to take them. Just shout in your microphone and I'll stop. Okay, so let's then get to some basic observations around the partition function that will lead us to implementing these things, these fields. So the first thing is that what we'll do is we fix some vertex of the graph, and we'll write the partition function as a sum of two parts, where we fix the vertex to be plus, and the other one where we fix the vertex to be minus. This is of course trivial, but it's good to make sure that we understand the notation. And then there's a basic lemma that if lambda has absolute value 1, then the absolute values of these two parts are equal. And so the reason for this is the following: that if your lambda is on the unit circle, then the conjugate of lambda is just 1 over lambda. So if I look at lambda to the power n, which this is just another number of norm 1, and then look at the complex conjugate of this guy, this also doesn't change the absolute value. And then I will see that this is in fact equal to this guy, showing that these two absolute values coincide. So what happens if you do that? So you multiply by lambda to the n, and then you have this lambda to conjugate to the number of plus assignments. And then, well, since lambda conjugate is equal to the inverse, I can replace this by a minus sign, and I can take this lambda to the n, I can take that inside. So I get an n minus n plus sigma. And now I can just, because this b to the number of edges receiving different signs is invariant under switching the signs. So what I'll do is I'll just switch the signs, and this one gets a plus, and this is essentially the number of minus signs. So then I'll just flip that again, and then I'll get just lambda to the number of plus signs. So this is equal to ZV plus, hence that these two guys are equal in absolute value. And this is somehow a very nice, it's like kind of like a one step further saying that you can, that z of 1 over lambda is essentially equal to z of lambda. So that inside the unit disk is like equivalent to outside of the unit disk. And this is somehow one step further. All right, so the consequence of this is that if we assume that the partition function is non-zero, then this ratio, that zg plus over zg minus, this is going to be on the unit circle. And I will use the notation s to the 1 here for the unit circle in the complex plane. And this is convenient to have, because we'll have a lot of, it adds a lot of structure to our problem. Okay, so we'll have this ratio on the unit circle. And so now what I want to do is I want to explain this idea of implementing fields. And so essentially what we want to do is we're giving a partition function which is guaranteed to be non-zero. And instead of saying that I can approximate the exact partition, or I can compute the exact partition function, I want to show that I can compute this ratio exactly. And of course, we're not really there yet, because computing ratios is not clear that this is sharply hard, but then we do a couple of other steps, and then we say, hey, we can compute something which we know is sharply hard. But let me just, the main step is somehow to be able to compute this ratio exactly. Assuming that we have an algorithm that computes the absolute value of a partition function approximately. So the idea is, so we write this ratio, which we know is on the unit circle. So we have this expression, this is e to the I alpha. And which just means that the z plus is this e to the I alpha times z minus. Let me just mention that. And so what I now assume or suppose so I will make good on my promise later, is I take my vertex V, and so this has a field of lambda associated to it, and I want to multiply this field, this external field, by e to the I theta. So that just means that if I have my graph, and if you think of the partition function as something multivariate, so every vertex has its own activity, then my vertex V will have activity lambda times e to the I theta. And all the other activities stay the same. You should think of this as a multivariable function in that sense. And then if I compute the associated partition function, I'll denote it by z hat, then this results in multiplying the z plus by this e to the I theta. It just shifts it a little bit. And so I multiply the z plus by e to the I theta, but if I choose a particular choice of theta, in particular if I choose pi minus alpha, then the z hat will become 0, because the z plus has this particular form. And okay, so this, if I would somehow be able to, if I could find this theta, then I could understand. So then I could understand when this is 0, and then this automatically would also determine alpha, and this would determine for me the ratio. But of course I cannot find this theta because I don't have any reason. How should I be able to find it? So what happens? I also see that there's something on the chat, by the way. Let me check for a second. Will is asking, what about -1? I will get to that at a second, somewhere towards the end, if that's okay. So what happens if I vary my theta, this absolute value of this z hat is going to increase to some point, and then it's going to start decreasing. So what I want to do is I'll just sample, like, I don't know, take 20 thetas equally spread on the circle, and then I'll compute each of these absolute values approximately, and then I see if they, what pattern do they follow, and then based on this pattern, I can somehow narrow down the location of the right theta. Then what I do again, I'll split that interval where I've narrowed it down, I split it up in another bit, and then I start doing this trick again. It starts increasing and then starts decreasing, or the other way around, and then again further narrow down the interval, and then I do some binary search, and then I'll locate a very tiny interval around the right theta. And then what we do is that we use the fact that we're dealing with lambdas and b's that are rational, or rational coordinates, so to speak. So this function, this ratio cannot have too many, cannot behave too wildly. And then somehow, if I have narrowed down this theta enough, then this should pinpoint me the exact ratio that I'm looking for. All right, so I should tell you this implementation of this field by some number. I should tell you how to do that, because now I'm just I'm kind of like did something which may not be allowed, because I say I can approximate this number, but this is not necessarily input of the algorithm of the problem that we care about, because this is a graph for which all the vertices have field lambda, but one of the vertices has another field, so that's like cheating. So we should I should tell you how to do that. Okay. So what we do is we take a rooted tree, and then implicit fact is partition function of this tree with lambda, zt lambda b, where the lambda and the b are as always. And this partition function is non-zero. That's not very difficult to see. So we can look at the ratio where we put the root vertex to plus divided over the root vertex to minus. And what we do is we glue this tree, we glue this to this vertex v. And that's going to have the effect, essentially the effect of implementing this field parameter. So let me tell you this. So if the resulting graph I'll denote by G prime. And then if I look at the partition function of ZG prime, so what happens if I set my vertex V to plus, then I'll just get the ZG V comma plus times the value for the ZT. And if I set it to minus, I'll get ZG V minus times the value of ZT V minus. But then if I divide on both sides with the ZT V minus, then here this guy disappears, here disappears, and here I'll get this e to the I theta, because it's this ratio over here. So by gluing trees along the vertices on the specific vertex, I can somehow change the vertex activity of this vertex to the ratio of this tree. So I would be in business if by using, and we use a tree of degree which has a root degree 1, so that it doesn't blow up the degree of this particular graph. And there's a little bit of stuff that I'm sweeping under the carpet, but that's not essential. So what I would want to do is, I said in the previous slide, I said I want to take these thetas, like I want to spread them arbitrarily around the circle, and then I want to do this binary search, and I want to keep doing that and keep doing that. So essentially, I should be able to get any point on the circle if I want to do this binary search. So what I would have to prove is that the ratios for these trees, they will get dense on the unit circle. That will be sufficient to make this approach work. Let me check the time. Okay, so that's essentially the second part of the approach, and that's looking at these ratios of these trees. And so the main theorem there, and that essentially says, if you look at the ratios of trees of bounded maximum degree, they lie dense on the unit circle. And this is really the heart of the paper, and that took us a lot of effort to prove. In order to say something about the proof, I need a definition. I think I gave the same definition last year. I spoke about zeros of the Ising model. So what we need is the notion of a Cayley tree, and that's just a tree which has, I'll just build it iteratively. The first one is just a single vertex. The second one has 2 layers. The third one has 3 layers, and we have down degree, a constant down degree at every step. And then if we look at the ratios for these Cayley trees, then so if I look at the ratio for the Cayley tree at level D, then I can express that as a function for the ratio at level level K. I'm sorry, D is not the level, D is the degree, K is the level. I can express that as a function of the ratios at level K minus 1. And this is just a simple trick by doing the Z plus and the Z minus, and noting that the tree has D subtree is going down, and they are independent. So you get this factor D in the exponent. And then we divide everything by a same quantity, and you get this function. So let me give this function a name. I'll call this R plus B over BR plus 1. And F, which is going to be the function that describes the ratio for the Cayley trees, is going to be lambda times G of R to the power D. And then, so where am I? This was here, sorry. And then, yeah, we need some properties of these functions that are going to be useful. So first of all, we easily see that this is a Möbius transformation, and it's not very hard to see that it preserves the unit circle, it also preserves the interior, and it also preserves the exterior. This in particular implies that F, which is just a div power of G, times multiplied by lambda, preserves orientation, and that's very, very important. And what we also have for this function, that if my B, this value is inside this interval 0, delta minus 2 over delta, and I take my degree to be delta minus 1, so the Cayley tree will have actually maximum degree delta in this case, then this map F behaves chaotically. So what does chaotically mean in this setting? It means that the derivative is lower bounded by 1 for all elements of the circle. So what can I do in that case? So I've drawn the circle here. So what can I do? I can take a small interval. I can apply f to it, and then since the derivative is lower bounded by 1 or strictly lower bounded by 1, it will expand. And also, since it preserves orientation, it will move forward, and then I'll move again, and then I'll map again, and then it starts expanding and expanding. And so let's go like this. And then what you see is, and it cannot expand indefinitely. I mean, it will have to cover the unit circle at some point. So what does that mean? That if I take this interval here and somehow I have built ratios for trees. So let's say that I can somehow build ratios. I have a tree T here that gives me a ratio inside this thing. Then what I do, and if I glue this tree to this Cayley tree, and then here once more, and then I'll go up, then essentially I'm propagating the ratios of this tree. I'm propagating that through this by applying this map fd applying this map d, and hence I will get ratios inside here, which are still ratios of trees. And so what I want to do is, so this essentially tells me, okay, the only thing I need to do is to make use of this chaotic behavior, is to somehow get density in some small interval, and then just use the dynamics to expand and to get everywhere. And
so could you remark on why? I mean, the condition on B, the endpoint, that's a closed interval, right? But then you get a strict inequality out of it. Is
so
that
the
something
point
I should be surprised by? Or?
So the point is, this is true for every number but 1. So this will be, the derivative is exactly equal to 1 at the boundary of this interval.
Okay.
But then, since it's so the derivative is increasing if you move along the circle, then as soon as you move away from 1, then it will be bigger than 1.
Okay.
But indeed, it's a kind of a subtle point that at the boundary you have to be careful. Okay, so so what I said is that we have this. What we want is to find an interval where we get density with these trees, and if I get that, then I can just do the map fd and apply that to that, and then this will correspond to a tree construction. And to get density on an interval, I figured I want to give you some idea of the techniques that go into it. So I will focus on the case delta is equal to 3. So that's like the most basic case. And so I'll have this interval 0, 1 over 3. And the assumption is then this implies that the second map, F2, is already chaotic. So the derivative is lower bounded by 1. So in a sense, to construct these trees, I can somehow only use F1. One that's not entirely true, but I'll get to that in a second maybe. But if I want to, then so I have two maps. I have 2 trees. I can somehow do this. I can make long paths that corresponds to iterating F1, or I can do this, which corresponds to iterating F2. And I can also do something else, but I'll get to that in a second. So if I look at the map F1, because it corresponds to these paths, then what is known from basic theory of Möbius transformations is that there exists some parameter lambda, such that if I want to make this green, if my parameter is on this arc, then the associated function will have an attracting or parabolic fixed point. While if the parameter is on this part in the complementary arc, then the map will be conjugate to an irrational rotation. And being conjugate to an irrational rotation just means that you can pre-impose just means that the behavior of this thing is already, it is like an irrational rotation, so that the forward orbit will become dense on the circle. So that's somehow nice. And in this situation, when we have this attracting or parabolic fixed point, the situation is as follows. You have some fixed point R, R1, and starting at 1, you will converge towards this fixed point. So if it's attracting, you will converge quickly. If it is parabolic, the convergence will be rather slow, but still you will converge from this side to this attracting, to this fixed point. All right. So that's something that we'll use. Okay, so that's information we have on this map F1. Now there's two cases. If for some magic reason the parameter lambda that we have is such that this function F1 is conjugate to an irrational rotation, then I claim that we're done, because what we do is we just start iterating, and then with F1, so we're just making very long paths. And the ratios of these paths, they will become dense on the unit circle. So that's good news. Okay, so that case is covered. So the other case is that this F1 is not conjugate to this irrational rotation, but it has an attracting or a parabolic fixed point. And then we have to do more work. Actually, there it becomes more fun. And then in case 2, we have to somehow distinguish two cases. We first look at this fixed point, and then we have to distinguish. We distinguish the case: is this fixed point? Is it such that is it inside this? So let me make this interval more clear. So we have this interval lambda 1 and 1 over lambda 1. So this is this interval where this associate map had an attracting fixed point. So if this R0 is beyond that thing, then that's either it's beyond this interval or it lies in there. So I'm only looking at the case where this attracting fixed point or parabolic fixed point is beyond. So what we do then is we take a path and we start iterating, and we start applying this path until we hit some parameter xi, which gets close to this R0, which is beyond this lambda 1. Okay, so this is a parameter xi, and what we do is we kind of cheat a little bit. We're gonna take, we want to implement, so we were dealing with the function f1 over f1 and f2 lambda, but now we want to change this lambda to this xi. And the way we do that is at every vertex of our path, this is the long path we have, and at every vertex we glue a copy of the path that corresponded to this xi. And so we do this for this vertex, and that has the effect of implementing this xi. Now I have to be careful because I think I made a mistake here, because probably this has the effect of implementing lambda times xi. So I didn't prepare this super carefully. So let's just sweep that under the carpet for now, and try to get the main message. Is by implementing this this path here, we change the vertex activity, and hence we change the map. And now this map has a parameter such that has a parameter xi which is beyond this interval. So hence it is again conjugate to an irrational rotation, and hence working with this map f1 comma xi, we can again get density on this entire unit circle. And what we also see is, because these paths are just paths, that the maximum degree of the graph doesn't blow up. It's still at most what it should be. So that's somehow good news. And then there's one final case, and I'm also looking a little bit at the time here, which is probably the most subtle case. So I'm going to skip that. Because already you see that there's quite a bit of technical ingredients, and this is only for the case delta is equal to 3. So let me go to the wrap up of the proof overview. So essentially what we do is, so we had this case delta is equal to 3, and we could somehow play with these two maps, f1 and f2. And if we, in a general case, we'll have to play with all of these maps, and somehow we want to get we want to find an interval, we want to find a sub-arc where we get dense, and we kind of do this by a very sophisticated induction procedure. And in this induction procedure, we make use of some number theory, some elliptic curves, and this is actually to get, this gives us the conjugate to this irrational rotation thing. And it's kind of subtle that because the parameters that we use are rational, the resulting map is conjugate to an irrational rotation, and that somehow follows from some elliptic curve argument. If somehow our parameters would have been maybe algebraic with bounded degree of the minimal polynomial, then maybe for all but finitely many parameters, the map will be conjugate to an irrational rotation. So there's some subtle number theory underlying this. And then, of course, there's some basic Möbius transformation. We also need some deeper complex dynamics than just this chaotic behavior of this map FD. And then there's another construction, some kind of like we do a contour set-like construction to guarantee to do some other stuff. So it's kind of like there's a lot of stuff going into the mix, and it took us a lot of time to make it happen. And we really wonder whether there's not a simpler argument to get density on this unit circle. And in fact, what you can prove from basic complex dynamics is that you'll have, if you just look at the map FD, so F delta minus 1, this will, if you start iterating it, so you start iterating this map, and this has a lambda associated to it, and you just look at the orbit of this map, so see where it goes. Then for a dense set of parameters, lambda, the orbit will be dense on the circle, but there's no guarantee that this dense set of parameters will have rational coordinates. So we kind of know, like, it's like just looking at the orbit of this thing might be enough, but it's going to be very tricky to prove that. And yeah, so we had to dive into some of the more detailed aspects of these things. So that's what I wanted to say about ingredients of the proof. Now I want to go back to this question of zeros versus hardness. And so last year when I spoke about zeros of the Ising model, I also talked about some complex dynamics, and I also said that chaotic behavior somehow implied the existence of zeros. And this is somehow the same is true for this hardness, because an essential ingredient was to use the fact that this map is expanding, this FD map, so that we can make these intervals bigger and bigger and bigger. And so both underlie the existence of these zeros and this density of these fields and the consequences that we get hardness. But somehow there's a subtle difference in the sense that for the hardness proof we have our lambda as a fixed input and it has rational coordinates, and we cannot somehow perturb lambda a little bit and just say, oh, we'll just work with some lambda close to it and we'll just do it with that, because that's of course not, then we're proving hardness for some other lambda. And while with zeros we can perturb actually lambda. And so we just look at this family of maps that sends lambda to the nth iterate of the d lambda map, even starting at lambda, and this is and then we can use this, and this is somehow the reason that we can do that makes the zeros proof almost a few lines. Well, the hardness proof is like, I don't know, 20 pages or so of a very complicated induction, which is, or maybe somebody comes up with a better proof, and then I'm not saying anything here, but so far it is 20 pages. And so this backs the question. I mean, so getting back to this, the theme, the starting theme of this talk is that, okay, so absence of zeros implies efficient algorithms. existence of zeros seems to indicate hardness, but is it really the existence of the zeros, or is it this underlying phenomenon of the chaotic behavior of the dynamical systems that indicates the hardness? I leave it to you to decide what you think, what you prefer. So was it? Yeah. So I have an idea, or I have a feeling what I think is the right answer, but I don't want to speak it out loud yet. I would like to go to some open questions and problems, and maybe before I go there, I can address Will's question, who asked, so yeah, what is the complexity about approximating the partition function at lambda is equal to -1, which is a real point on the unit circle. Yeah, so what we showed is that it's equivalent to approximately computing perfect matchings. So it is it's not sharply hard, but it's still yeah, yes, maybe unresolved. Maybe that's the best way to say it. Yeah, so I showed you in the beginning this zero freeness result, that if this is not right here, this should be interval 0, or this should be a different interval. There should be an endpoint to this interval, and this is -1. So if B is in this interval, I showed you this result that we had this arc where you have zero freeness, and what we also show in our paper with Hannes, that on the complementary arc the roots are dense, and yeah, so this leads of course to the question is, what is the hardness of computing the partition function on the complementary arc where there are zeros? And so we tried analyzing that, but somehow we failed so far, and we suspect that it's hard. And we suspect that the way to prove it is using this dynamical behavior. But in our proof, we make use of the fact that the derivative of these FD map is lower bounded by 1, and we kind of lose this property if we go on this complementary arc. So that's kind of annoying. And finally, I want to make a few remarks about the independence polynomial. I promised this in the beginning of the talk, so I think I've seen this picture in another talk this week, or a variant of this picture. So this is, say, the prototypical picture of the locations of the zeros of the independence polynomial. So the green thing is the Scherer disk. This is, I don't know what this is. This is something which Peter Chikvari and Ferenc Benz proved. This purple thing although it goes all the way up to the Regts bound, this is due to Han and myself. And this blue cardioid-shaped thing, the interior of this doesn't contain any zeros for these scaly trees. And what we proved is that roots accumulate on the boundary of this object. And so so we asked the question, so what is the hardness of what's approximating the independence polynomial? And then Bezakova and Goldberg and Galanis and Stefankovic proved that it's indeed sharply hard outside the cardioid. And so far this seems like a good picture. So zeros, no zeros. Of course, inside here we don't know, but at least on the outside we do know. But then my student Piotr Buys found actually curves cutting inside into the cardioid, and with roots, how do you say that? Arbitrarily close to the boundary of these curves. So there are roots cutting 4 bounded degree graphs. So they're not Cayley trees, of course, but they're like some clever combination of alternating layers, like level, like down degree D, down degree D-1, and then clever combinations. And these curves, they cut into the thing, and somehow like destroying the beautiful picture that's there. So it's much more complicated than yeah, we initially hoped. And so when we started our project, we actually wanted to prove that it's hard to compute the independence polynomial in the boundary of the interior of these curves, so like cutting inside here. But we didn't manage to do so because I don't know because of what. Maybe we're not clever enough. In any case, we didn't manage to do so, and then we ended up proving this stuff for the Ising model. But here, really, the connection between zeros, dynamics, and hardness and efficient algorithms is still, I would say, rather open, and probably it's going to be a very complicated picture if it's going to be resolved at all. Yeah. So with this, I'd like to thank you all for your attention, and yeah, that's it.
Thanks a lot, Guus. This is really nice talk. Any questions? Okay, so I have one question. So is there any need to prove a bound on the rate at which the these roots that you get from the Cayley trees become dense? Because the trees get bigger, right? And they're part of the input. So, I mean, is your error that you're shooting for a constant, so it doesn't matter? Or is it, if it depends on n, then you have to control how fast it becomes dense, right?
Yeah, that's a good question. I think here, so because of we have a given lower bound on the derivative, I think you can easily see how quickly you expand and you'll cover the circle. So I think you can probably it goes pretty quickly, like log n. Maybe it goes like log n.
But do you need? I see. But you actually use that in the proof, I guess, because
No,
you need the trees to be not too big, right?
We don't say anything about the size of the trees. I mean, so what question do you ask actually? Is it for the zeros or for the hardness?
For the hardness. So
yeah,
you need the trees to not be huge, right?
Yeah, definitely. So the trees are going to be constant size.
Okay.
Essentially.
Yeah.
Yeah, I think that, yeah, so given, so they're going to be, where you have your input graph and your input lambda and b, so they will determine the size of the inputs. And so all these trees that we compute somehow are independent of the inputs. So they're really, I mean, the size is going to be huge, but they don't depend on the inputs.
Yeah, they only depend on the error that you get at the end, right?
On the epsilon, so like the density parameter that you
okay, and no, but I mean, in your reduction, in the end, you showed that if you could compute this, you could compute something exactly, right?
Yeah.
But I guess you don't really mean exactly. You mean like 1 plus epsilon or something.
No, this exactly is really exactly because it's a rational. This ratio has rational coordinates, so you can somehow. It's like you should think of it as a lattice point in some very huge space, and if you get close enough to a lattice point, then it can only be that lattice point.
Okay, but then don't you need to be able to choose very fine values of theta? And then you need a very good bound on how quickly these trees give you thetas that are dense on the circle?
So that's a good question. Yeah, so you don't need very fine bound, because the trick is that it has this increasing, decreasing property. So you get, so let's see. Yeah, so I think if I recall correctly, I think the bounds that we need on the theta are not, they don't depend on the, well, I have to be careful here. Saying that they don't depend on the. Yeah, so I would have to like dive into the technicalities of the proof. So I cannot tell you by heart right now what the dependence actually is, but
you can get whatever you need basically. So
yeah,
it's fine. Yeah. I guess one more question is, so you had to do a lot of work because you needed this to work for rational lambda. Because of the input model. Would it become much easier if the input was given as a root of an algebraic, like an algebraic number, like just as a root of some polynomial? Like, could you suppose you worked in the symbolic model of computation where you could represent numbers via their minimal polynomials?
Yeah, so then you wouldn't get an exact algorithm for computing this ratio. Then you would get a very good approximation. Mm-hmm. But I think other than that, except maybe there's some subtleties with with some of the with this being that this particular Möbius transformation is conjugate to an irrational rotation, because it also somehow depends on the input parameters, and rationality gives that they are conjugate to irrational. If they're algebraic, then there's only a finite set of them for which they're not conjugate to an irrational.
Okay, but then you have to worry about what that is and stuff.
Yeah, and then yeah, so that's a little bit, or a possibly finite set, and then you would have to either try to find out, prove that it's not, that the finite set is empty or not, and that's somehow we were able to do that in the rational case, but for algebraic we figured, okay, this is gonna give us too much headaches.
Okay, so it doesn't make your life easier, is the point. It makes your life harder to do algebraic.
Harder, yeah. And also it doesn't, it's not, because that's still I mean, somehow it would make our lives easier if we would say, okay, we'll just we take the lambdas for which the forward orbit of this expanding map covers has a dense orbit, and that would make our lives very easy, at least for that part of the proof. But then, of course, we don't know anything about these lambdas. So if they happen to be algebraic, then this would make things easier.
I see. Yeah.
There's it's very hard to say anything there, I think.
But presumably, if you wanted to prove hardness in some real number model of computation, then you could try that route. You need to find some other hard problem in that model, whatever that is.
Yeah, so you would maybe, it's not clear what if because here we really make use of the fact that if you get close enough to a rational number, then with finite, with bounded number of bits, then you have to be that number.
Yeah, you need some approximation hardness for some.
There are very few hard problems in the real model.
I see.
Basically one.
And which is that?
Well, solving a system of polynomial equations.
Okay, I see.
Yeah, so I think that would be tricky then to reduce to that. I don't see that as a possibility.
It's a question. So do we know what happens for the anti-Ferromagnetic Ising model, but fields off the circle?
So what the question is for the anti-Ferromagnetic Ising model, and then lambda to be off the circle?
Yeah.
No, to be honest, we don't. We have looked at it, and I think at least the reduction part probably goes through, but somehow, so we looked a little bit at what happens on the circle, and there you can prove some stuff on the circle, but we thought it's kind of like the circle is very restrictive because we don't really know where the zeros are, but there's some results on them, so we kind of didn't know where to look for what lambdas to play with, essentially. And I think a lot of this work could go through, although the fact that the associated transformations no longer preserve orientation make things more difficult.
Yeah.
But then again, that would still be if you're on the circle, and if you're off the circle, then it would even be more difficult. But maybe at the same time, it could be easier. Yeah. So yeah, don't fully know, but I think definitely part of this will definitely could go through. Yeah, there's a lot of space for the anti-ferromagnetic regime.
Yeah.
And yeah, so yeah, I think the reason that we didn't look at it because we didn't really know what would be the best, best place to look, or well, yeah, what would be nice to know? What would be nice to know that's hard, or what we don't. But yeah, so if you have any.
So one more.
Yeah, please go ahead.
So on the real line somehow, so the complexity drops. It's also like for the hardcore model, for example, and for the anti-Ferromagnetic Ising model, we know this phase transition, and there is NP hardness for approximation on the real line. And at least for the hardcore model, we know that just as soon as you move up, it becomes number P hard, like the approximation problem also.
Yeah.
I mean, yeah, that's just a phenomenon. But is there another explanation for it, or sort of,
Yeah.
it's not a very well-formed question, but
No, but I think it's a very good question, because I actually did start thinking about especially the hardcore model, and but then you know that the dynamics beyond the lambda critical, then you just have a attracting orbits so beyond lambda critical, and that's not chaotic behavior, of course. That's still good behavior from the complex dynamics perspective.
Yeah, it just goes to infinity, or something like that.
And so I mean, it will still attract things, and but somehow, yeah. So somehow it's still the fact that it doesn't converge to a fixed point, but that it has this alternating behavior.
Yeah.
Somehow people still manage to get hardness out of that. Yeah. So I don't have. Yeah. So maybe because it's not chaotic behavior, if you would get chaotic behavior, then definitely. I think Sharpie hardness seems reasonable, because you can somehow get anywhere.
Anywhere, yeah.
Anywhere you want, and you can somehow implement anything in principle, and that is a good indication that you for Sharpie hardness, and maybe and this other reduction is maybe more refined, or it's more subtle maybe. But yeah, somehow I feel like this. Sorry, I didn't quite get what you were saying. There was a bit of noise on the line.
No, it's not. Did you were saying something, right? So I just thought.
Yeah, I somehow feel like that, like this underlying dynamics has something to say in all of this, but I don't fully, or very far from any reasonable understanding to the claims there.
And one final comment, which is more of an apology. So this independent set picture, there is some updates to it, which I think Jan already announced last year. And we in fact finished the write-up last year, but we have someone never got around to updating it. We have been updating it this week.
Yeah, that's very good. I mean, you mean this picture, right? Yeah, so that there's some stuff. Yeah, let me draw it. There's some stuff here.
And also like actually, yeah, it goes. You can even extend a little bit on like as far high up as the sequari area, the bench sequari area. Yeah. And you get.
Yeah, I somehow forgot about it. I knew about it, but then.
No, it's our fault because we never uploaded it. So but now we will in soon. Yeah, so we suddenly woke up last week to finish that.
Good to know. I'll look forward to reading it.
So I mean, this might be a naive question, but is there some intuitive reason why this should be hard at lambda equals 1?
Lambda is 1. So what do you mean?
Not this, the Ising model. I mean, the Ferromagnetic Ising model at lambda equals 1.
It's not hard at lambda equals 1.
Oh, it's not hard. Okay, good.
No,
it is a randomized algorithm, but there's no deterministic algorithm. No.
Okay.
It's easy probabilistically.
And maybe somehow our result could say that looking for zeros is well, already you know that the zeros accumulated 1, but that arbitrarily close to 1 it is hard. So somehow you would have to look at it from a different angle maybe.
Yeah.
To the deterministic algorithm.
Yeah. I suspect that 1 is easy somehow because zeros are rather symmetric, right? You're squeezing in between two conflicting zeros. Something like that.
Sorry. Yeah, there's one interesting thing about the randomized algorithm at lambda equal to 1 also is that it does not actually work at lambda equal to 1. What you have to do is to perturb lambda a little bit to lambda equal to about 1 over n, then run the algorithm there and just argue that lambda equal to 1 over n gives you a good enough approximation. So by 1 over n, I mean 1 over poly n. So depending upon the approximation you want, you have to perturb lambda by that much and run the algorithm there. The algorithm does not work at lambda. In fact, the Markov chain that you use is not connected. But you can also do random cluster as Heng is saying. So that's just okay. So that's maybe okay. That doesn't. Yes, what I was saying is not true for that dynamic. But for the first group, the Jerome-Sinclair group, that Markov chain is not even connected at lambda equal to 1. You have to perturb it slightly and run it there. But the perturbation can be so small that you can actually just get a good approximation.
Yeah, so in a sense, this lambda as 1 is a hard point in that regard.
Yes, but as Heng was just pointing out, random cluster does not have this problem, and recently random cluster was proved to, like Heng and Mark Jerem to convert to be fast converging.
Yeah, so maybe if you want to do it deterministically, you have to also go via the random cluster model, maybe.
Yeah. Yeah.
Or maybe, I mean, it sounds like the first resolution was that you do 1 over poly n. So maybe this problem, I mean, in this correspondence between hardness and zeros, maybe you want to say, are there zeros in a disk of radius 1 over poly n?
Yeah, I think that is.
Because the problem is robust to moving by 1 over poly n or something, right?
Mhm.
Or, I mean, okay, you need to qualify it more than that because you could just move away from the circle. But I mean, yeah. I see. Great. Well, thanks a lot. So I guess tomorrow's the last day and see everybody tomorrow.
Yeah, thanks. Bye.
Thanks.